Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at electrodes and electrode theory, and in the last class we looked at some fundamentals of bioelectricity and how bioelectric potentials essentially form the fundamental aspect of life, and how about 25 to 40% of the total energy of the body is used just to operate the sodium potassium pumps. So much must be the importance. That shows nature's commitment to these electrical activities. They must be evolutionarily important. Now let's consider one aspect of or one type of these signals that is universally prevalent to diagnose heart related symptoms. It is called as electrocardiography. So in this class we will look at electrocardiography and we will look at the block diagram of the ECG system. Going forward, instead of saying electrocardiography, I will simply be using ECG throughout the rest of the lectures and the rest of the course. So what is ECG? ECG essentially records the electrical activity of heart, but the heart is a mechanical pump, is it not? The heart physiology, cardiovascular physiology, the detailed cardiovascular physiology is beyond the scope of this class, but briefly, oxygenated blood reaches the left atrium and deoxygenated blood reaches the right atrium, and when the atria contract, the atrioventricular valves, there are two such valves, one is a bicuspid valve, the other is a tricuspid valve. These two valves open and fill the ventricles, and after the ventricles fill, the ventricles start contracting. As the ventricles contract, the pressure on the arterial valves, the aortic valve and the pulmonary artery valve open and lead to ejection of oxygenated blood from through the aorta and deoxygenated blood through the pulmonary artery. This is the brief overview, extremely brief overview of the physiology of the heart. Now, from all this what we know is that the heart is a mechanical pump. It fills with blood and then it pumps blood, but then how does it contract? First, atrial contraction will have to happen for the ventricles to be filled up with blood, then the ventricular contraction will have to happen, so blood can flow through the aorta and the pulmonary artery. So that is essentially mediated through the excitable nature of the cardiac muscle. There is exactly one muscle in this type of muscle. There are different types of muscles: skeletal muscle, smooth muscle and cardiac muscle. These are the three major, one way of classifying muscles. In cardiac muscle there is exactly one muscle, the heart. It is a single muscle and it follows a particular rhythm of contraction, and all of the entire heart beats in sync, in a functional sync. This is also called as the functional syncytium. Functional syncytium for the heart. Now exactly how does that work? That is the question for us. So this electrical activity is naturally transmitted from what is called as the natural pacemaker of the heart, also called as the sinoatrial node. This is the sinoatrial node in this picture. From the sinoatrial node, conducting cables or conducting fibers conduct to the atrioventricular node or the AV node, that is the atrioventricular node. the AV node. There is a brief pause at the AV node to wait for the ventricles to be completely filled up. So, there is a delay, and then through the from the AV node there are two bundle branches. These conducting fibers branch out into two sides. This is called as the bundle of His, and then there are two bundle branches. These are called as the left and the right bundle branches, which then branch out further into the so called Purkinje fibers. Much really teeny tiny fibers that innervate practically every cardiac cell. Every heart cell is innervated by these conducting fibers. So, this rhythm of the heart is of course mediated by the activity, health and several other factors. Now, throughout there is this electrical activity that starts from the sinoatrial node, and then through the conducting fibers reach the AV node, and through the bundle of His and the bundle branches branch out into the Purkinje fibers and practically innervate the entire cells, all the cells of the heart. This electrical activity can be detected because it generates an electric field that can be detected outside the body or on the surface of the body. This is a rhythmic repeating signal, but the rhythm will vary depending on the activity, state of mind. For example, if you are anxious or if you are tensed, then the heartbeat will increase. If you are relaxed and rested, the heartbeat rate will be low. Also, if you are doing some physical activity, the heart rate will be high, and so on and so forth. So, there are multiple things that determine how fast or slow the heart will beat. This is essentially a rhythmic repeating signal that is generated by the heart or the electrical system of the heart. And when you measure it from outside, this can be represented as a time varying electric dipole. So, any deviation from the expected waveform essentially indicates a cardiac abnormality. So, this is how we measure or we detect, we diagnose the health of the cardiac tissue. It turns out that this is one of the most successful biomedical instruments in the world that is present practically in almost all primary care centers. All nowadays, for example, even in India, all primary care centers have an ECG machine. So, this is an example of a commercially and scale wise successful biomedical instrument. So, if you are interested in building a medical device, you need to keep a device such as the ECG system as your benchmark for scale. Such is the scale at which this is deployed, because it turns out that even primary care physicians can read ECG and can detect abnormalities. Of course, maybe they will not treat abnormal or patients who show abnormalities, but they will refer them to the cardiologist. Now, it turns out that that's that prevalent and that widely adopted. So, this is one of those most successful medical instruments. Yes. Why is it important? Critically, what it shows is the connection between the electrical activity of the heart and the mechanical activity of the heart. It turns out that electrical activity precedes the mechanical activity, or first the electrical activity happens and then the mechanical activity happens. There is a small, relatively brief, what is called as a electromechanical delay. Some electromechanical delay is there, because it is beyond the scope of this course for me to teach how electrical activity is getting converted into mechanical action, sarcomere function. It's beyond the scope of this course for me to teach, but do look at my other courses in which I have taught how sarcomeres contract. It takes a finite amount of time for this contraction to happen, because at the molecular level there has to be cross bridges that will have to be formed and then pull. Of course, the heart sarcomere is more special than the regular skeletal muscle sarcomere, but that is a matter of detail. Anyhow, coming back to the electrical system of the heart, we have the sinoatrial node, which is the natural pacemaker of the heart. This is there naturally. This is not the pacemaker device that is implanted. This is the natural pacemaker that is already present in the heart. The implantable pacemaker is what we keep in case the sinoatrial node fails. In future videos, in future weeks, I think in the 8th week or 9th week, we will look at pacemakers and various types of pacemakers in good detail. Right. Here we look at the natural pacemaker, which is the sinoatrial node. Right. Where is it located? It is located on the right atrium, near the vena cava. What is the vena cava? Vena cava is the largest vein in the body. Vena cava branches out into two, one that goes below the heart and one that goes above the heart. The one that goes above the heart is called, of course, the superior vena cava, and the one that goes below the heart is called as the inferior vena cava. Again, beyond the scope of this course, but do check this. I expect the students of this course to know this. And this sinoatrial node acts as the heart's primary pacemaker, the natural pacemaker of the heart. It is about 3 centimeters, 2.5 to 3 centimeters in length, and about 2 mm. That is a relatively thin slice of tissue. At rest, it beats at about 72 beats per minute, but then this varies as a function of cardiovascular health. If you are a sedentary person, at rest also it might be beating at above 80. Or if you are an athlete, if you are an endurance athlete, for example, you quite literally have a big heart. That is literally enlargement of the heart so much that much lesser number of heartbeats are enough to pump heart to the entire body of, for example, endurance athletes such as marathoners. 60 beats per minute may be enough at rest. This impulse spreads through the atria in about 100 milliseconds, about 0.1 seconds. So, what you find, what is generally called as the ECG, is the graphical recording of the electrical activity of the heart, and it is measured using surface electrodes that are kept. Where are they kept? The primary electrodes are kept on the right arm, forearm, and the left forearm and the left leg. Okay. But then there are also some other electrodes that are kept on the chest, called as the chest leads or the precordial leads. Depending on how you take out the signal from these connections, you can also have what are called as augmented limb leads. We will come to that in a little bit. Sometimes, to avoid noise, the right side, the right leg is given feedback of the noise, common mode noise. This is called as a right leg driven system. We will dedicate an entire video to this system. So, this is measured using surface electrodes. In general, the frequency range is between 0 and 100 hertz. Amplitude is in the ranges of millivolts. Essentially, what you observe is that first there is a P wave that signifies atrial depolarization. Depolarization means, remember when we discussed action potentials, we discussed what is depolarization. Becoming more positive. atrial depolarization will be followed by atrial contraction. This is atrial depolarization, this will be followed by atrial contraction. This atrial contraction is then followed by a brief period of lull or rest, and a very brief period of rest, followed by a septal depolarization via the bundle of His, septal depolarization, followed by the beginning of the ventricular depolarization. This ventricular depolarization is then followed by ventricular, I am writing ventricular contraction or the ventricular systole. Of course, the atrial contraction is called as the atrial systole. Systole means contraction, diastole means relaxation. So, this QRS, this QRS essentially signifies the ventricular depolarization, and at around the point when you reach S, depolarization has happened through all the Purkinje fibers. The Purkinje fibers are those that innervate, they are really small and innervate the maximum number of, a large number of cardiac myocytes, right. This is followed by ventricular repolarization. Several questions emerge. Sometimes this is also followed by Purkinje fiber repolarization, another U wave that is not shown here. Several questions follow. We have spoken about ventricular repolarization. What about atrial repolarization? Atria have depolarized and then followed by ventricular depolarization. So, that means the first atria has contracted, followed by the ventricular contraction. But then before the ventricles can relax, the atria will have to relax. That means that atrial repolarization must happen, but that is not actually shown. That happens around this time. That happens during the QRS complex. This is also synced with the atrial repolarization. Note the words DE depolarization versus RE repolarization. Atrial systole happens after atrial depolarization, whereas after atrial repolarization what you are having essentially is a diastole, right. So, this is the typical, this PQRST is the typical ECG waveform. Now, a question is, another question that comes is why is the depolarization of ventricles and the repolarization of ventricles both have positive amplitude in this graph? That is a question. We will come back to that in a little bit. Meanwhile, there are some timing related parameters that I could study. For example, the PR segment, the duration, how long it takes between P and R, how much time it takes for P and R to happen. The QRS segment, how long does the QRS segment last, and how long does the ST segment last. Also the PR interval, this is the PR interval, this is the QT interval, time duration between the end of P and the beginning, before the beginning of Q is the PR segment, and this relaxation period between the end of S and the beginning of T is the ST segment, but then between Q and the end of T is called as the QT interval and the PR interval. All these things have physiological significance. Okay. Here is a typical block diagram of a ECG system. You have a lead selector that have multiple electrodes, only 3 electrodes are shown here. You have a lead selector, and then through the lead selector the data from or the analog signal from the lead selector is sent to a pre-amplifier, then this signal is sent to a power amplifier, and then there is a frequency selective feedback network that chooses the gain of the power amplifier. This output of the power amplifier is then fed to a bridge output circuit, which then operates the pen motor. This is the typical and then there are two. So, essentially the output of the ECG is written through a pen on a chart that is rolling at some speed. So, there is a chart transport motor that is there, and then there is a pen motor. There are two motors, one moves the pen, the other moves the chart, and the output is essentially like a graph sheet on which the QRS the entire ECG signal for various leads is measured and printed. The output is a hard copy print. There are also digital ECG, there are also digital signal processed ECG and all those things that are now prevalent, but the most important, the most critical is the one that is used in the primary care setting is the paper pen or the chart and the pen based ECG system. These potentials are picked up by the limb electrodes and taken to the lead selector switch, and you can choose which of the leads that you want. Do you want lead 1, lead 2, lead 3, or the augmented limb lead or the precordial leads and this. And in the lead selector, the electrodes are selected 2 by 2 according to the program. Which one you choose, depending on that, only those will be printed. The pre-amplifier will have 3 or 4 stage differential amplifier system having relatively large negative current feedback from the end stage to the first stage, which means that the output will be relatively stable. So, essentially that is the preamp. This amplified output signal is then picked up single ended and then sent to the power amplifier. This is the push pull differential amplifier. The output of this power amplifier is also single ended, that is fed to the pen motor, which essentially moves the pen, which deflects the writing arm on the chart. Usually this sort of a direct writing recorder is adequate for the primary care setting that is there, but there are also other more digital forms, that the ones that can store and then do some pre-processing, and those forms are also available. ECG signal of interest has limited bandwidth, so usually a digital a direct writing recorder is sufficient and adequate for the purposes of, at least for the purpose of primary care settings. This frequency selective feedback network is essentially an RC network that provides the damping to the pen motor, that is preset by the manufacturer, so that it is not too fast, it does not oscillate too much, that it produces too much noise. There are other auxiliary circuits that provide a calibration signal, 1 millivolt calibration signal, and then automatic blocking of the amplifier during a change in the position of the lead switch. So, when I am changing the lead switch, at that time there is the amplifier is blocked for a brief period of time. It essentially also it may include a speed control switch. So, the chart motor is controlled by these auxiliary circuits, and the pen motor is controlled through these frequency selective feedback circuit. There is also a standby mode of operation that is provided, in which mode stylus moves in response to the input signal, but the paper itself is stationary, paper does not move, the stylus alone moves just to check. This essentially allows the operator to adjust the gain and baseline, to adjust the system a little bit without wasting paper. If the paper is also moving, pen is also moving, then a lot of paper will get wasted. So, this is another mode, right. So, with this we come to the end of this video. In this video, we looked at the typical PQRST ECG signal and a block diagram of the ECG system. With this, we come to the end of this video. Thank you very much for your attention.